Morning, everybody. We're going to continue looking at radicals and exponents today. And so we're going to focus more on the exponent side of things. And so to start today, we're going to start by looking at the basic patterns of exponents. So we are going to be continuing in section 3 in that red book. And the first thing that we're going to do is we're going to examine some patterns of exponents. And what we're going to do is we're going to look at number 6 on page 70 there, and basically try to evaluate a pattern with the powers of 3 here, just to refresh us on some exponents and hopefully figure it out here. So what we're going to do is we're going to look at 3 to the first power, 3 to the second power, 3 to the third power, 3 to the fourth power, 3 to the fifth power, so on and so forth. And we're going to try to look for a pattern to find the last digit of 3 to the 101st power. So as a reminder of what exponents are, they are just telling you, so 3 to the first power just means 3. It means 3 multiplied one time, which is 3. So the last digit there would be 3. If we look at 3 squared is 3 times 3, which would give me 9. If we look at 3 cubed here, that would be 3 times 3 times 3, which would give me 27. So the last digit there is 7. Last digit there was 9. Last digit there was 3. We're going to look at 3 to the fourth power now, which is 81. And then let's look at a couple more. 3 to the fifth power, if we multiply that by 3, that would give me 243. And if we look at 3 to the sixth power, that would be 729. And so one of the things with exponents is you can use these to figure out patterns about numbers long term. So if we want to figure out what the last digit for 3 to the 101st power is, what we need to do is we need to look for a pattern. So with an exponent of 1, the last digit was 3, and then it went 9, and then it went 7, and then it went 1. And this pattern here is actually going to be cyclical. It's going to keep repeating itself. So every 4 terms, so 1, 2, 3, 4, the next one is going to repeat the pattern. It'll be 3, 9, 7, 1, 3, 9, 7, 1. So if we want to know the last term in 3 to the 101st, the last digit, not the last term, what we can do is we can apply that pattern long term. We can say, okay, well, 101, how many cycles through that would that be? So that would give us 100. So 100 is 1 before that. So in 100 powers, there would be 25 cycles of 4 here. And then we'd be on the first step of a new cycle. So we'd be essentially on this step right here. So we'd say, well, the last digit in each of the first one, because it went first, second, third, fourth, first, second. So if this is the first one, it's going to end in a 3. So the last digit here is 3. Now, you may have to use a computer to verify that, 3 to the 101st power. The last digit is 3. I do not believe a calculator or a iPhone would do that accurately. It would probably use scientific notation, which is what we'll look at the end of this. But that's just a thought problem to start us off on exponents. So what we're going to be working on today really is going to be working on a bunch of simplifying exponents using what are called the laws of exponents. And so you all have probably reviewed these at different points in your math career, but I just want to refresh you on these so that we can apply these here in just a second. So if we've got a to the m power times a to the n power, what we do to simplify that is we combine those powers. And the way that I want you all to think about this is that x squared means x times x. That's x squared right there. If we multiply it with 3 more x's, x times x times x, we have to think, what exponent would I use to denote that? So there's 5 x's being multiplied total there, so we would call that x to the 5th power. And that is the reason that property is what it is. So then, if we're looking here, if we've got a to the m divided by a to the n, again, these are just some numbers. If they got the same base, what we can do is we can subtract those powers. So if we've got b to the 3rd power, and we've got divided by b to the 5th power, the way that we're going to rewrite that is we're going to say b to the 3rd minus 5, and then we're going to say that's b to the negative 2. And we'll expand on that in just a little bit. We'll expand on that in just a little bit there. Now, when you've got an exponent to an exponent here, you got a to the m to the n power. Mathematically, the way that you simplify that is that you multiply those things together. That's the shortcut. Now, the way that you actually put this into practice, if you read this, it says b squared to the 4th power. Well, that means that we've got b squared 4 times. And if we multiply those together using that first property there, we've got 8 b's we're multiplying in total. So that would be b to the 8th power. And we also have an exponent rule that says if we have an exponent outside and we've got two terms on the inside, we want to distribute that term evenly to each. So we distribute that to each term there. So what we do in practice here, so if we've got 3x to the 4th squared, so the reason that we do that, there's 2 of these things. There's 3x to the 4th times 3x to the 4th. And what we would do is we would simplify those. Well, there's 2 3's. That's 3 squared, or 3 times 3, which is 9. And then x to the 4th times x to the 4th is x to the 8th. So you don't have to write it out each time like this. I just like to do that to remind you all where these exponent rules come from. I think we can fall into a trap in mathematics of not thinking about where these things come from and just randomly doing things. I think that is a bad trap to fall into. So I do like to make it explicit. Now, for these fractions here, for a divided by b to the m power, we can still distribute those. We can still multiply those. So if you had 2x squared divided by 3y, and that is to the 3rd power, we would say, well, that's the same thing as 2x squared over 3y times 2x squared over 3y over 2x squared over 3y. And essentially, we're just cubing it. Like we could have very easily just distributed that power, but I want to write it out, be obnoxious with it. So 2 times 2 times 2 is 8. X squared is x to the 6th. 3 times 3 times 3 is 27. Y times y is y cubed. So now, typically my experience with students is in these last two, the first 5 properties are pretty easy to follow. There's sometimes a little bit of a disconnect with these last 2 properties. So pay attention here when I'm going over these. So anything to the 0 power, if something has an exponent of 0, it evaluates to 1. And the reason that is because if you look, it has to do with this subtraction property that we used up here. So if we've got x cubed divided by x cubed, you all know that anything divided by itself is 1. However, we can also use this subtraction property up here to rewrite that as x to the 3 minus 3, which means that's going to be x to the 0. And since this right here is the same thing as x to the 0, we know this divided by this is going to give us 1. That means anything to the 0 power should equal 1. And then similarly, this last property here, a to the negative m, equals 1 over a to the m, this negative exponent property here that some people have trouble with. The way that you can do this, you can write this one of two ways. The first way is that you can write out all of these x's right here. X times x times x, 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 1, 2, 3, 4, 5, 6, 7. And if you cancel out those x's that you're multiplying, what you're left with is 1 over x squared. However, you could also rewrite this using that subtraction rule, x to the fifth minus 7 equals x to the negative 2. And both of these things right here are exactly equal, which means that this property right here holds true. And in general, the way that you're going to make a negative exponent positive is if it's in the numerator, you're going to move it up from the denominator. If it's in the denominator, you're going to move it up to the numerator. You're going to move it basically wherever it is not. You're going to take the reciprocal of it. So that is a run through those properties, and we're basically going to be spending the rest of this video practicing these properties. So the first thing that we're going to do, we've got some expressions here that we are going to express as powers of 2. So the first thing we're going to do is represent 16 here. So we're like, all right, 16. How can we represent that as 2? Well, 16 can be 4 and 4. 4 and 4 can be 2 and 2 and 2 and 2, using a good old factor tree here. So we can reduce 16 for expressing it as a power of 2 as 2 to the fourth power. So then if we wanted to represent 1 over 16 here, if we wanted to say 1 over 16, the way that we could do that, we just established that 2 to the fourth was 16. We could write that as 1 over 2 to the fourth. Or think to your second about that property that we just went over. You could also see this represented as 2 to the negative fourth power. Either one of those would be perfectly fine. So then this 1 right here, using those exponent properties, think to yourself real quick. How can I represent 1 as a power of 2? How do I get a power of 2 from 1? Well, the way that I get that is by having 2 to the 0 power. 2 to anything to the 0 power will give you 1. Now, we're going to get a little bit trickier here, just a little bit trickier with the algebra in these last two. So right here, we're going to look at the expression 4 times 2 to the n power. Now, looking at that 4 right there, we want to write that as a power of 2. So you should be thinking to yourself, well, what 2 to what power gives me 4? Well, that's going to be 2 squared times 2 to the n. Now, the thing is here, I want this as a single power. So think to yourself real quick. When we've got multiplication of powers, what do we do with those exponents? So what we do is that we combine those exponents. So we're going to write this as 1 power 2 to the 2 plus n power, which is, we don't know what n is, which is fine. Now, we're going to do the same thing here on e. So I want you all to try this one yourself real quick. I want you to try this one yourself. So let's see, we've got 2 to the m over, we can express 8 as 2 to the third power. And what we can do from there is we can say, okay, well, since these are dividing each other, we're going to say this is m minus 3. So this is 2 to the m minus third power, or m minus 3 power. So just a little bit of algebra manipulation there. And that's largely what we're doing today. We're working within these exponents to simplify. So the next thing that we're going to look at example 13 from page 73. So if you're wanting to reference those, you are welcome to. So the next thing that we're going to work on is expressing these in exponent form with a prime number base. So the first one we're going to look at here is we're going to look at 9. So we need to think, okay, how can I express 9 in terms of a prime number? So we should be thinking, okay, well, 9 is 3 to the second power. So what I'm going to do is I'm going to replace that 9 right there. I'm going to say 3 squared to the fourth power. And from there, I'm going to say, well, 3 squared to the fourth power, that's actually just 3 to the eighth power. So now we've got a prime number to a power. A little bit easier to work with, a little bit easier to simplify. So then on B here, well, we can kind of do the same thing. We can write this out as 3 to the x over, this is going to be 3 squared to the y power. And when we've got an exponent to an exponent, to simplify that, what we're going to do is say, okay, well, that's 3x over, if we distribute there, 3 to the 2y. And to finally reduce that, when we are dividing, think to yourself real quick, how can I rewrite division of exponents? And the way that we do that is with subtraction. So again, we don't know what x is, we don't know what y is. We are just writing an expression. And so then for the last one here, I want you all to rewrite 25 to the x real quick using a prime number. So take a second and try that on your own. So 25 is 5 squared there. So I'm going to rewrite that as 5 squared to the x. I'll distribute that, 5 to the 2x, and we are good to go there. We are good to go. Now, we're going to continue using these properties because it's been a while since we've used them. I want to make sure that we are good to go concerning them. So if you're like if you want to try these without Mr. Price going over them, you probably can do most of these without my explicit help, and that's okay. I will not be mad. So the first one we're going to simplify here, we've got 4x cubed times 2x to the 6th power. So that 4 times that 2 is going to give me an 8. X cubed times x to the 6th is going to give me x to the 9th. Because we're multiplying those, we're going to add those powers up. So on B here, we've got division. So again, with division, it's easy to think about how many of these t's are going to cancel out ultimately. So if I got 7 t's up here and I've got 5 t's down there, I'm going to end up with t squared, because 5 of those will cancel, but you can also just subtract them. And 15 divided by 3 is going to leave me with a 5t squared. So then on C here, again, when you're evaluating exponents or simplifying them, you should follow the rules of simplifying these things. So if you got exponents to exponents, be sure to distribute there. So we've got k squared times k to the 6th here over k to the 6th. That's going to give me k, so let's see, 2k's times, okay, I'm multiplying 8 in total over k to the 6th. And then from there, if I've got k to the 8th over k to the 6th, that means 6 of those will cancel out to give me k squared. So again, just some pretty straightforward exponent work there. So we're almost finished for today. We're gonna continue our simplifying here. We're gonna continue to work within these things. So the next thing that we're gonna look at here is working a little bit with the negative exponents. They work the exact same way component-wise. I just want to touch on those just a little bit more. So if we've got 2c to the 3rd power to the negative 4th power, the first thing that we're going to do, we're going to distribute this just like you would a regular power. So we're going to say 2 to the negative 4th power, and then negative 4 times that 3. And so what that's going to give me here, let's see, that's going to give me 2 to the negative 4th, c to the negative 12th power. And as a general rule of thumb, we like to express things without negative exponents. So as a reminder to that law, that exponent law that we went over earlier, if you've got a negative exponent, the way that you make it positive is to write it as 1 over that number. So what we're going to do to make these things positive is we're going to write 1 over 2 to the 4th power, c to the 12th power. And then we're just going to clean up that 2 to the 4th power because that can simplify a little bit better. So 2 to the 4th power, 2 times 2 times 2 times 2, 16 c to the 12th. And that is the simplified version of that. Now, on B here, where we've got a negative exponent up top and we got a negative exponent down low, as a general rule of thumb, to make a negative exponent positive, what you're going to do is you're going to switch it. You're going to flip the spot of it. You think about that law where it moved from the numerator to the denominator. If it's in the denominator, to make it positive, we'll move it up. So to rewrite this thing, b squared is going to be chilling up here. But this c to the negative 1 is going to move up just as a c, because if it's a positive exponent, we do not write that power. And then we're going to bring a to the negative third down, so it's a to the positive third. And as a general rule of thumb, we like to keep things in terms of positive exponents because to evaluate a negative exponent, you have to make it positive anyways. So save yourself some work on the front end. So then the next thing that we're going to look at here is we're going to try to express things without fractions. Typically, students don't like working with fractions. Typically, it makes our lives easier if we do not have to work with fractions. So we're going to try to do our best to avoid working with fractions. So here, if we've got 1 divided by 2 to the 1 minus n, we need to think about how could we get that out of our denominator. So we're going to basically go in reverse of that negative exponent there, where we've got the fraction and where we worked to get to here and then back to here. We're going to work in reverse of that. So we're going to say 1 over 2 to the 1 minus n. This is equal to 2 to the 1 minus n to the negative first power. To the negative first power. And what we can do is we can just distribute this thing. If we decide a fraction, we'd rather work without fractions. So we can say 2 to the negative first power. Well, that's going to be 2 to the negative 1 plus n. But again, when you're writing expressions, we like to make sure that the variable comes first. So we'll say 2 to the n minus 1 there. And this is the exact same expression as what we had over here, but now we don't have to evaluate. If we want to substitute in a number, we don't really have to work with a fraction. We don't have to work with a fraction. So a couple of other things to note here, a couple of other things that we can look at. We're going to look at 2 more where we try to express these things without fractions. And then we'll look at a little bit of scientific notation and we'll call it a day. So we've got 2 expressions here that we've got as fractions. The first one, we've got x squared plus 3x plus 2. And this whole thing is being divided by x. And so whenever you've got something dividing a bunch of terms like this, one of the properties of fractions is we're allowed to break this up into individual fractions here. We got x squared over x plus 3x over x plus 2x, or not 2x, excuse me, 2 over x. And there's a lot of usefulness for this later on in mathematics of simplifying this way. But what we can do is say, okay, well, x squared divided by x, well, only one x is going to cancel out there, so we'll have just x. Here, those x's will cancel out. We'll have x plus 3. And then here we've got 2 over x. But our thing is we're trying to write this without a fraction. So if we've got an x in the denominator, to get it out of the denominator, the power here is 1. We're going to move it up to make this 2x to the negative first power, just to get it out of it being a fraction. Depending on the situation, it may be more beneficial to have it as an exponent versus having it as a fraction. So that just depends on the situation. So we're going to look at one more example here. So we've got 2x to the fifth plus x squared plus 3x, and this is being divided by x to the negative second power. And so the way that we can rewrite this, we want to write this without fractions. This x to the negative 2 is dividing this whole thing. If we move this up, it's going to go from dividing this whole thing to multiplying all of these terms right here by x squared. And so really all that we've got left to do is to distribute this x squared term. It's going to make our life just a little bit easier. So what that's going to give us, 2x, let's see, 2x squared times x, that'll give me 7x as we're multiplying. X squared times x squared will give me x to the fourth. And then plus 3x cubed. And that is the last thing for simplifying exponents. And I would be remiss if I didn't give you all a little bit of application for some of the exponents that we just talked about, that we just learned. And so the very last thing here is something that you all are probably a little bit familiar with, is this concept of scientific notation. And so typically you use scientific notation to represent numbers that are very, very large or very, very small. And it kind of saves you some writing, because it's called scientific notation because typically in science you can run into some very large numbers or some very short numbers. So instead of writing an entire number out, you want to write it in shorthand. So the way that you do scientific notation is we have a times 10 to a power, where a is going to be a number between 1 and 10. And again, we see this notation pop up here. And k is so the way that you read this right here, k is an element of the integers. Somebody decided to use z as our number for or as our symbol for integers. So that just means it has to be a positive or negative whole number. And so really the way that you write scientific notation is you look in your number and you say, where could I put a decimal point so that I would have a number in between 1 and 10. And so if I'm looking at 37,600, I'm looking, if I put my decimal point here, it'd be like 37.6. So I want to put it right here for 3.76. And what I do is I say, okay, well, how many times would I have to move that decimal point over to the right? So 1, 2, 3, 4. So what we're going to do is we'll say this is going to be 3.76. Now, I don't know if you all think about it this way. To move the decimal place to the spot one, every time that you do that, you're multiplying something times 10. You think about like what's 3 times 10 is. It's 30. You move that decimal spot on 3 over 1. So when you write scientific notation, every time you move that decimal to the right, you're multiplying times 10. So we've got 4 multiplying times 10s here. So that's going to be 10 to the 4th power. This is the scientific notation for this number right here. Now, in the same way, for big numbers, where 10 is going to be a positive number, when you've got a smaller decimal, when your number is less than 0, or not less than 0, less than 1, but between 0 and 1 rather, what we're going to do is say, okay, I'm going to look to see where I could put this decimal point to get a number between 1 and 10. So if I put it right here, and every time that you move a decimal place to the left, you're multiplying by 1/10 or you're dividing by 10, whatever way that you want to think about that. So times 1/10 times 1/10 times 1/10 times 1/10 times 1/10. So 1, 2, 3, 4, 5, 6 times. So the way that you're going to see this written is you're going to see it 10. So where we've got that happening 6 times, they're going to say to the -6 power. Now, from what we've talked about today, you could also express this as the equivalent of that would be 8.6 times 1 over 10 to the 6th. But when you see scientific notation, they're going to use that negative exponent. I need you all to understand that these two things right here mean the same thing. So that is all that I've got for us today over exponents and over scientific notation. So if you all have any questions, please let me know. I'll be available on Zoom or through email, and we can figure something out together. But thanks, everybody, and you all have a good rest of your day.